Lesson: Supervised versus unsupervised learning, key differences and use cases. Supervised and unsupervised learning are fundamental concepts in the field of machine learning, each serving distinct purposes and offering unique advantages in the development of intelligent systems. Understanding these two approaches is crucial for professionals aiming to harness the power of artificial intelligence to automate workflows and optimize decision-making processes. The key differences between supervised and unsupervised learning, along with their respective use cases, provide valuable insights into when and how to apply these methodologies effectively in real-world scenarios. Supervised learning involves training a model on a labeled dataset, meaning each training example is paired with an output label. The primary goal is to learn a mapping from inputs to outputs, enabling the model to predict outcomes for new, unseen data. This approach is akin to a teacher supervising the learning process, guiding the model through corrective feedback based on known outcomes. Supervised learning is particularly useful for classification and regression tasks. For instance, in a classification problem, such as email spam detection, the model learns to distinguish between spam and non-spam emails based on features such as sender information, content, and frequency of certain words. In regression tasks, like predicting house prices, the model learns to estimate continuous values based on factors like location, size, and amenities. Several practical tools and frameworks are available for implementing supervised learning. TensorFlow and PyTorch, two popular open-source libraries, offer comprehensive ecosystems for building and training machine learning models. TensorFlow, developed by Google, provides a flexible and scalable platform for deploying machine learning applications, while PyTorch, developed by Facebook, is favored for its dynamic computation graph and ease of use, particularly in research settings. Scikit-learn, a Python library, is another essential tool, offering simple and efficient tools for data mining and data analysis, built on NumPy, SciPy, and Matplotlib. It provides a wide array of algorithms for classification, regression, and clustering, making it a versatile choice for implementing supervised learning models. Unsupervised learning, in contrast, deals with unlabeled data. The model explores the underlying structure of the data without guidance from labeled outcomes. The objective is to identify patterns, groupings, or anomalies within the dataset. This approach is akin to a student learning without direct supervision, discovering insights independently. Unsupervised learning is particularly valuable for clustering and dimensionality reduction tasks. Clustering, such as customer segmentation in marketing, involves grouping similar data points together based on their features, enabling businesses to tailor strategies to different customer groups. Dimensionality reduction, like principal component analysis, reduces the number of features in a dataset while preserving its essential characteristics, facilitating data visualization and reducing computational complexity. K-means clustering is a widely used unsupervised learning algorithm that partitions data into K distinct clusters based on feature similarity. It iteratively assigns data points to clusters and updates cluster centroids until convergence. Another powerful technique, hierarchical clustering, builds a tree-like structure of nested clusters, offering a more flexible approach to grouping data. Tools like Scikit-learn provide implementations of these algorithms, allowing practitioners to experiment with different clustering techniques and evaluate their effectiveness using metrics such as silhouette score and Davies-Bouldin index. The distinction between supervised and unsupervised learning is not merely theoretical, it has significant practical implications. Supervised learning requires labeled data, which can be costly and time-consuming to obtain, but it offers high accuracy and interpretability when such data is available. Unsupervised learning, while not reliant on labeled data, often yields less precise results and requires careful interpretation of the discovered patterns. The choice between these approaches depends on the problem at hand, the availability of labeled data, and the desired outcomes. Real-world applications of supervised learning are abundant and diverse. In healthcare, supervised learning models assist in diagnosing diseases by analyzing medical images or patient records. For example, a deep learning model trained on labeled X-ray images can accurately detect conditions like pneumonia, aiding radiologists in making informed decisions. In finance, supervised learning powers credit scoring systems, predicting the likelihood of loan default based on historical data. Similarly, in the field of natural language processing, supervised learning enables technologies like sentiment analysis, where models classify text into positive, negative, or neutral sentiments, providing valuable insights for businesses monitoring customer feedback. Unsupervised learning also finds numerous applications across industries. In cybersecurity, anomaly detection algorithms identify unusual patterns in network traffic, flagging potential security breaches. These algorithms learn the normal behavior of a system and detect deviations, enabling timely intervention. In retail, unsupervised learning facilitates market basket analysis, uncovering associations between products frequently purchased together, informing product placement and cross-selling strategies. Additionally, in the realm of genetics, unsupervised learning helps identify gene expression patterns associated with diseases, advancing our understanding of complex biological processes. The integration of supervised and unsupervised learning can further enhance machine learning applications. Semi-supervised learning, a hybrid approach, leverages both labeled and unlabeled data, offering a balance between accuracy and data availability. This approach is particularly useful when labeled data is scarce or expensive to obtain, allowing models to benefit from the abundance of unlabeled data. For instance, in image classification tasks, semi-supervised learning can significantly improve model performance by utilizing a small set of labeled images alongside a large corpus of unlabeled ones. The effectiveness of supervised and unsupervised learning is influenced by several factors, including data quality, feature engineering, and algorithm selection. High-quality data with relevant features leads to more accurate models, while poor quality data can result in biased or misleading outcomes. Feature engineering, the process of selecting or transforming variables to improve model performance, is a critical step in both supervised and unsupervised learning. Techniques like one-hot encoding, scaling, and normalization ensure that input data is suitable for model training. Algorithm selection is another crucial consideration. For supervised learning, choosing the right algorithm depends on the problem type, dataset size, and computational resources. Decision trees, support vector machines, and neural networks are popular choices, each offering specific advantages and trade-offs. In unsupervised learning, the selection of clustering or dimensionality reduction techniques is guided by the nature of the data and the desired insights. To address real-world challenges effectively, machine learning practitioners must adopt a systematic approach to model development. This involves defining the problem clearly, selecting appropriate data sources, pre-processing data to handle missing values or outliers, and iterating on model design and evaluation. Tools like Jupyter Notebooks facilitate this process, providing an interactive environment for data exploration, model prototyping, and result visualization. In conclusion, supervised and unsupervised learning are foundational concepts that underpin a wide range of machine learning applications. Understanding their key differences and use cases enables professionals to make informed decisions about which approach to adopt in various scenarios. By leveraging practical tools and frameworks, such as TensorFlow, PyTorch, and scikit-learn, practitioners can implement these methodologies effectively, addressing real-world challenges and enhancing their proficiency in the field. As the demand for AI-driven automation and decision-making grows, mastering these concepts will be essential for those seeking to become certified AI workflow and automation specialists.